I don't, okay.
So next talk is Analysis and Vulnerabilities in zkLogin, and Sofia, Celi will give the presentation.
Yeah, thank you. Okay, let's wait for the slides. Okay, thank you very much. My name is Sofia Celi, as it was said, and today I'm going to be presenting kind of a paper that we developed on trying to analyze a specific system that has been deployed in production, which name is zkLogin. And this talk is going to be very applied, so expect less of a theory, but more about the vulnerabilities that we found in production in this specific system. And this is joint work with my co-authors, Hamed Haddadi and Kalden Hartog. Okay, and if you're interested in reading more about our research, I invite you to click the links on this slide if you further want to read, or also to read our blog post. Okay, so specifically on this talk, we're going to be talking about a system that had been deployed in production, and we have analyzed it from many perspectives. We have analyzed it both from the paper perspective, from the code perspective, and also we have performed some reverse engineering on the code because some parts of the codes were not public, and we need to reverse engineer to understand further how the protocol works. And specifically on this specific talk, we're going to be talking on specific types of systems, which are usually called zero-knowledge attestation systems. What are these systems? Are systems that want to attest of something from a specific users, so later you can use that specific attestation to further authorize some actions. And what we want to know when we actually started this research and analyzing this specific protocol is we wanted to know what it means to actually deploy them, under which security model, under which assumptions from users, and how can they fail in practice. And this is not a slight against zkLogin. It is really cool cryptography, but it's just to tell you that we're putting something in production or doing the protocol design, you have to be careful. Okay, as I told you, we're essentially looking at these specific types of protocol, which we have called ZKA systems or zero-knowledge attestation system, which is what they are, what I just told you. Essentially, what you have is a protocol that uses ZKPs in order to attest something. For example, that the statement is true about a specific document that has been, quote-unquote, committed to, that can be an external byte stream, so we can use that specific attestation to later authorize certain actions. So if you're familiar in the web, for example, you can use a ZKP of certain documents to later say like, oh, this specific human is not a bot, this specific user is not a bot, hence authorize that this specific user can later perform some actions on the web. In the case of zkLogin, they are doing this by having an external document, which is a signed JSON Web Token, a JWT, and the action that they're trying to authorize is that they can perform transactions later. Okay, and as I said, in theory, they seem to be straightforward, but in practice, they can kind of fail. Okay, and why we want this? Again, because maybe we want to give the ability to users to be able to attest to something, so they don't have to be presented to actually present the document all the time. So we don't want to actually to have a system that is cumbersome to users. But at the same time, we don't want to go against the privacy of the users. So these systems are both usable in that the users don't have to be presenting a document every time. And they're also privacy preserving because we're attesting everything in ZKP. It has many design and applications, and indeed, if you have watched some previous talks and some previous research, some of the systems that are already proposed to be used, as for example, zkTLS or zk authorization, zk middle boxes, zk compilation, can be kind of a flavor of this zkA attestation system. Okay, just to keep in mind, what we are actually trying to do is that we're trying to attest about some statements that we know that exist in an externally crafted document. And something that we will argue in this talk is that it's not enough to only say that that specific statement exists in this specific document. So let's think about the concrete case of zkLogin. In zkLogin, as I told you, they are going to be using signed JSON Web Tokens, JWT, that usually have this form, as you see in this slide. They have a key, and attached to the key is a value, and they can have nested claims. But what we argue is that in ZKP, you don't only have to attest that indeed this statement exists, but you also have to attest that this specific document conforms to the JSON grammar and to the JWT rules. Why is this the case? You will see later when we actually see the vulnerabilities. Okay, so this is zkLogin, and I understand this is a very kind of like complex diagram, but we are going to be looking at it under detail. So first, let's introduce what the protocol is. As I told you, zkLogin is just an example of a ZKA system. And what they want to do is to leverage the fact that users already authenticate to external services, to, for example, to Google, to Google, and the return of that specific authentication event is going to be a JSON Web Token. So what they're going to do is to use the fact that they already have a JSON Web Token to walk through it and do a ZKP of that specific JSON Web Token, and later use this fact, this attestation, to authorize further actions. In this case, the actions that they want to authorize is to authorize transactions. As you already see in this slide, the specific system is already based on JSON Web Tokens, which means that in turn it's based on a specific federated protocol that is called OpenID Connect, or OEDC. And essentially in OpenID Connect, you have the set of parties that you see here. You have an issuer, so think about it as Google or Meta or whatever external big issuers. You have an application or a website that wants the user to authenticate to, but this specific website doesn't actually implement all of the authentication mechanisms themselves, but rather they leverage the fact that users might have accounts in another websites already. And you also have an external prover and an external source service, and a user and a verifier. The verifier is not so interesting, so we're just going to kind of ignore it in this talk. This is how OpenID Connect works. You essentially have, as I told you in the previous slide, this set of parties. In the case of OpenID Connect, you're going to be having only a subset of those parties, so these 3 parties. You have the user, the relying party, which is the website, and then you have the specific user, which we also call it the OP. And what happens is that you can try to log into a website, right? And the website tells you, hey, I don't implement authentication myself, but I'm going to forward your request to OpenID Connect. Then it forwards the request to a specific external issue. Then that specific request is forwarded to that external issuer, so for example, Google, Meta, or whomever else. And the return of that specific interaction is going to be assigned JWT, as you see here. And eventually then the relying party says, okay, now I know that you really log in with that specific external provider, and hence I know that also I can create an account for you in my specific service. So what is important here is that the parties that you carry in OpenID Connect are only the user, API, and OP, but then zkLogin is going to be adding 2 extra parties, an external prover and an external source service, and also a verifier. How does a JWT look? A JWT is just specifically this document that we actually decompose it in 3 specific sets. So we have the header, the payload, and the signature. The header is just like a specific statement that contains like metadata information about that specific document, as for example, telling you, hey, I'm using this specific algorithm that I'm going to sign in this specific JWT. It also tells you, for example, a specific claim that is called the key ID, which essentially tells me this specific signature is signed with this specific signature algorithm, and the specific key that I'm going to be using is the one that I determine in this specific field. Why is this the case? Because many issuers might be having many public keys, and hence you have to actually determine under this specific key, this specific JWT has been signed. You also have a payload that has a lot of claims, as we call it in JWT. The ones that are mandatory are the issuer claim, the subclaim, the audience claim, and the expiration claim. The expiration claim is kind of like, you can understand it by yourself, it's just like an expiration, and it's very short, because if you have ever talked with any security expert or any hacker, they will tell you that using JWTs in production is really dangerous because they are really easy to extract them from local storage in the browser and use them to impersonate other users. This is going to be kind of like one of the core vulnerabilities, or one of the base stones for the vulnerabilities, as we will see later. But as I told you, you also have other claims. You have the issuer claim, which is just like an identifier to say like, hey, this is a JWT issued by Google. You also have an audience claim, which is exactly a specific string that the issuer has assigned to that specific application. You also have a subject claim, which is essentially a string that says this is the subject under the namespace of the issuer. So think, for example, that your issuer is Google, then a specific subject, for example, is going to be the email of the person under the namespace of Google. So it's going to be Gmail, for example. And then you have a signature, which is just a signature over the payload and the header. And the key that you use in order to sign this specific signature is going to be the one that is advertised or in the metadata, which is in the header. Okay, so this is how zkLogin works. Now let's look at it more into detail. How does it work? Essentially, what we have is that you have an RP that will try to say like, hey, I want your user to authenticate, but I don't have the authentication way to actually manage to do that. So I'm going to send that request to an external issuer so you can authenticate. And if you authenticate correctly, then I can also say that you have authenticated to my system. First, what it happens is that the application that we usually call DRP generates ephemeral keys that we call secret key and the verification key, and it's going to be setting an expiration that we call tmax. Then it also locally generates a nonce, which is going to be the hash of the verification key concatenated with tmax, concatenated with a random value r. In this case, zkLogin uses this nonce as an unlinkability mechanism, because every time that you are having the verification key, you're exposing to the service that this is your verification key, so they're trying to randomize it with this specific random value r. This goes against the OpenID specification, because if you're familiar with it, you know that OpenID indeed allows you to, for example, add a nonce value in this specific JWT. But in OpenID Connect, this nonce value is used as a replay protection mechanism. On the contrary, here in zkLogin, it's used as an unlinkability mechanism, and it's really longer than the expiration time or replayability security of the JWT. This in itself is kind of a vulnerability. Then what happens is that a user using this specific application that we call DRP authenticates with the OpenID provider, so it sends the password, for example, to Google, and if it's successful, essentially what Google returns you is a signed JWT. Then the RP takes the JWT and asks for a salt from an external service, which is again used for unlinkability. Why? Because in zkLogin, your ZK address is going to be the hash of the subject concatenated with the audience, concatenated with the issuer, concatenated with the salt. And again, if we don't use a salt here, then it will be really easy to link transactions because they are using static elements. OK, so you generated the nonce, and then with all of these values, the actual application takes the JWT, the nonce, the verification key, the tmax, and the r and the salt, and submits it in fully to an external proving service. What does this proving service essentially do? The proving service then is presented with all of these values, and it says, OK, I'm going to try to verify and then prove in ZKP that this JWT is really well corrected, is well formed, it has been validated and really well created by an external issuer. So what they do is that they perform what we call an ad hoc selective parsing procedure. And this selective parsing procedure is only executed only for a single instance of some specific claims. What is this selective parsing procedure? As you remember, we use JWTs. We kind of conform to the grammar of JSON. What they do is that they walk this specific document, and what they check is that each substring of this specific document either ends with a comma or with a bracket. Then they determine that each substring has to have double dots in between, as you see here. And then they also determine that whatever is in front of the two dots is going to be called the key, and whatever is after those two dots is going to be called the value. And they also check that each one of these specific fields has to be a string because they use the double quotes. But if you're familiar with grammar, or with JSON grammar, or with JWTs, performing this selective parsing procedure is not enough. It's really easy to actually break the security by having a specific JWT that has some of these values changed, as we will see. OK, but currently we're just describing zkLogin, and that's what it does. It performs this specific selective parsing procedure, and then they attest in ZKP that this ad hoc selective parsing procedure was executed correctly, that the nonce value was computed correctly because they proved this specific hash function that generated the nonce, and they prove it in ZKP that it was generated correctly. They check the JWT signed by an issuer who publishes the keys, and they check also that the ZK address was generated correctly. And if everything is cool, you actually get from the proving service a specific proof. And you present that proof later to the verifier when you actually want to perform transactions in a blockchain context. OK. Now let's start talking about vulnerabilities, and here's kind of like the interesting part. So what does zkLogin assume? In their paper, zkLogin assumes that the backend services, meaning the prover and sold services, are untrusted, which is a little bit weird for me, at least from an application perspective, because you usually don't assume the backend services to be untrusted. But this is their threat model. They also assume that the OpenID Connect issuer, so for example, Google or Meta, is trusted, which is somewhat OK in a trust model. Then they further assume that the front end is trusted, which is really strange to me. And the claim of why this is trusted is because it is subject to public scrutiny. But because it is subject to public scrutiny, we will see later that it's easy to actually launch attacks against this specific front end. We don't think that this is actually a realistic threat model, and we think this is the starting point of the vulnerabilities, because again, you shouldn't really trust the front end to, for example, safely maintain secrets or secret key material, because again, anybody can publicly scrutinize that specific front end. We also don't think it's really reasonable to think that the external issuer should be trusted by default, because you're working in a federated system as it is OpenID Connect, and because a lot of research has actually shown that many even like really trusted issuers have historically generated malformed JWTs over time. So we don't think it's really that much of a really solid threat model. Okay, so let's look at the vulnerabilities. Remember that when I was explaining zkLogin, I told you that essentially what they use is an ad hoc selective parsing procedure. And here I showed you a JWT that subverts that. Why? Because you have, for example, duplicated claims. And if you're familiar with the JSON grammar or JWTs, you will know that the specific specification of JSON grammar or JWT is a little bit lax in this specific kind of details. So for example, the JSON specification as specified in the RFC actually tells you that it is okay to have duplicate claims, and that sometimes some applications choose to use only the first claim or sometimes the last claim. So it is unclear. But what happens in reality is that if you present this kind of JWT to a system as, for example, zkLogin, then one specific proof statement can be linking to the first instance of the issuer, and another one can be linking to another instance of the issuer. If you remember also, again, the ad hoc selective parsing procedure, you will know that they also only care that whatever was in the middle of that specific statement had to be some double dots. But they didn't manage to check, for example, that white space should not be allowed in between the claim name. Or, for example, you can easily even inject JavaScript in between a string, which is the value, and then execute that specific malicious JavaScript at the moment of parsing this specific JWT. Why this happens is because zkLogin is essentially using a grammar or like an unspecified grammar to actually perform validation of the JWTs. So it's really easy to shadow specific statements. It's really easy to inject the statements. It's really easy to even inject JavaScript in that specific JWT to subvert the system. One immediate question that you can immediately pose me is that maybe this is not a direct vulnerability, because in order to generate these malicious JWTs, you will have to have an issuer that is issuing these malicious JWTs and then signing those malicious JWTs. And you can tell me, like, do those issuers exist? And my answer to you would be, yes, they exist. And in fact, in the specific code of zkLogin, what we found out is that they accept issuers of this specific form that you see here, which is just an AWS tenant. And if you're familiar with setting up AWS, anybody can set up an AWS, which means that I can literally have a malicious issuer that just gives me maliciously created JWTs that I can use in the system. And the reason for this is because, first, because they are not really checking the correct parsing of the JWT in the system, and also because they are allowing really lenient issuers to be part of the system. Even more interesting is that not only the system accepts like malicious JWTs, but it also allows for cross-audience and cross-subject impersonation. Remember when I told you that the JWTs have a specific field, which was the subject identifier, which has to be, for example, a Gmail associated with the issuer, associated with Google. But because you have malicious issuers, it means that you as an AWS machine can then say like, oh, give me JWTs for this issuer that is Gmail, and indeed that can happen. And the reason is because we're never checking that the subject claim of the specific JWT is a correct one in regards to the namespace of that specific issuer. So you can literally create JWTs from a malicious issuer that are malformed and are also from a user that didn't even authenticate it with that specific service, nor even didn't even belong to that specific issuer. Furthermore, you can tell me, OK, that is very cool, but what about the secret storage of all of the keys that we just generated as part of zkLogin? Well, it turns out that in the specification of zkLogin, they recommend that any secret, including secret keys, salt, and nonces, should be stored in local storage. And if you're a developer, or you have worked more in a developer's perspective, you will know that this is really insecure. Why? Because anyone can actually check local storage and take away those specific keys and then reuse them for later. So essentially what we have here is that by setting an arbitrary AWS Cognito tenant, extracting, for example, the secrets from local storage, constructing a malicious JWT containing those specific malicious, for example, AOD and subject, and then signing under the AWS keys, you have a key that passes all validation and could be linked to another application and another issue. We disclosed these findings in November 2025, and we only received a reply way later. And then eventually we received another reply way later over Twitter. And it was argued that everything is kind of OK because they fully trust the external issuers. However, we push back, and they say that they are really going to have a proper parsing as part of their systems. We're still in conversation and actually pushing back that they should even push further and actually add even more validations in the system. So this is really cool cryptography. I'm not saying it is not, but when you actually put this into production, you really have to think carefully on the threat model and under which assumptions you want the system to use. And also, please don't rely on browsing insecure storage to secure your keys. I know that it is cumbersome, but please, there's other ways that you could actually store your secrets instead of like in the exposed front end of the browser. OK, and with that, thank you very much.
Any questions? Yes.
Oh. Okay.
Hi, thanks for the talk. I've been working for some time on like typically parsing in zero knowledge. And typically what we have is something like you can specify an arbitrary regular expression, and it gives you a zero knowledge proof that an input is parsed with this regular expression. If you have something like that, is this sufficient to rule out all the attacks related to parsing, or do you need something more?
No. So that's a really great question. So I have 2 papers actually on parsing on ZKP. So the first one that I will invite you to read is a specific paper that is called Reef, that literally does checking in ZKP regular expressions. And there's another one that we call Coral, which is checking parsing under context-free grammar. So it's usually not enough because not only you have to check the regular expression, but you also have to check some specific constraints of the language. So for example, that your claim is unique could not be really that well captured with a specific regular expression. And another thing is that specifically the protocol that we have that is the fastest to actually do parsing in ZKP still only works for context-free grammar. Here is sometimes not enough because you actually have to prove, for example, that the subject is the same under the issuer. So you have context there. So it is not a context-free grammar because JSON is not a context-free grammar, but you also have to check, for example, that certain specific strings have a dependence, some context dependence to other specific strings that belong into your specific document. So it's not enough with a regular expression. It's a good starting point, but you will have to expand it to first context-free grammars and then to context-dependent grammars. But I'm happy to send you the papers.
Yeah, a question here. I've been working with similar stuff like zkLogin. I call it zkOut. But the thing is, it's complex in the sense, so from my understanding, what I'm seeing here is that they try to modify the way OIDC works in some sense. So one of the questions from me is just like to understand, like, do you think that this can be done without modifying or reusing the existing RFCs? For example, even from a security standpoint, maybe using HYPE, like which is high assurance profile for OIDC. Like, what would you recommend? Do you think that it's necessary to make these kind of modifications to make ZK and OAuth work together?
So the first thing that I will say is probably not be reliant on JWTs. And this is, again, if you talk to any security experts, they will tell you that they hate passionately JWTs because all the time they are stolen. And if you store one JWT, you can easily use to impersonate other users. Per the specification of OpenID Connect, actually the JWT expiration times should be really short. Here in zkLogin, they're actually expanded that expiration time so they can reuse it almost indefinitely, which should be against the spec because, again, you can extract those JWTs and then use it as long as possible to impersonate users. So we'll say don't rely on JWTs. I know that people like auth, I know that people like OpenID Connect, but please let's not look at those protocols. But something that can work is if you rely in another protocol, which might give you like stronger assurances. So if you want, for example, to prove authentication, all that you can do is actually check that the return HTML from a TLS connection is the correct one, right? Like you try to log in, you send your post request, and then the return is like a successful authentication. You can prove that in HTML by leveraging already something as TLS. That is more in line to what zkTLS, for example, is doing. So we'll say that might be an interesting direction that already leverages the fact that TLS 1.3 has really strong security properties in comparison with JWTs.
Yeah. So in some sense, would you say that it's hard to be able to reuse? Because, for example, in my case, I'm just like trying to reuse as much as possible of the OIDC specs, the existing ones, so I don't have to create like a custom approach to integrations. And that's basically your suggestion. Like, well, you might need to create like a custom approach. So do you think that's?
Yeah, so that will be interesting. Currently, there's many discussions in the IETF that you can be part of if you want. Not specifically about zkLogin, but they're specifically looking at some similar systems for age assurances or for any other kind of assurances. And what they're trying to leverage is also maybe passing a document and then generating something as privacy pass tokens, which are unique and reusable. You have like a set of them, and then you just use them via one first authentication event. So something like that could be more interested. You will not have to modify that a lot, but you will have to convince the standardization people eventually to standardize.
Yeah, perfect. Thank you.
Any other question?
Hi, thank you. Do you need to do range checks on the scalars inside the payload? Or
Yeah.
Okay.
Okay, so here they don't do this because all of these are strings, so they don't actually pass that. But if, for example, let's say that this is a document that belongs to age verification, then you will have to prove both that that specific integer that is associated with that specific key is an integer and follows the rules of integer for a specific grammar, and also then that it's in the range via bulletproofs or whatever, so use a range proof to check that.
Cool. And then also, yeah, so is the expectation that these JWTs in the browser are ever used for value securing use cases, or is it only like read-only use cases?
It's only for read-only use cases. So the majority of times is for that. Like you authenticate with someone with a specific external service, and then you return a JWT, a short expiration time JWT.
Cool. Thank you.
Any other questions? Okay, while the next speaker is getting ready, maybe I would like to ask you to maybe summarize your recommendations, like in.
Okay. Okay, so looking at each one of the vulnerabilities.
Yeah.
So the first one is don't accept any arbitrary issue. You really have to have a trust chain that actually tells you for the whole system, this is the issues that we are going to be accepting. Think it to be similar on TLS. So for example, on TLS, it's not that we only accept every certificate authority, but rather the community has sat down and said, like, these are the certificate authorities that we're going to accept because we know they are not malicious. And not even that, if you're familiar with TLS, you know that even certificate authorities can be malicious, because sometimes you have some adversary that has broken into CAs and had actually created malicious certificates. That happened, for example, to Google in a case that allegedly Iran broke into the servers and actually managed to create malicious certificates. So you will have to have like a good root of trust to actually verify that all of these issues are not misbehaving. So that's the first thing. The second one, please don't put your secret keys on the browser. You can use backend services. You can use session-bound cookies. There's many ways that we can do this in the web, but don't expose them to the browser. Like anybody, any injected script, like malicious dependency, any person even that just looks and opens the dev tools will manage to extract that key. So don't do that. Then you also construct a JWT that cannot be arbitrarily malformed to accept any other audience claim or any subject claim. And also check that a specific subject claim belongs to the namespace of the issuer. So you know that if the issuer is Google, that the subject claim is Gmail, for example. So you have to check that correspondence. And then finally, I will also say that you have to actually verify that the audience claim is really the one that the issuer assigns to this specific application. So you have to have that trust be in all of the parties of the system instead of only relying that the specific application is giving you the correct values. That's it.
Thank you so much.
And also, yes, perform passing in ZKP also. Yeah.
Let's thank Sofia again. Okay. Next talk is about